What's happening, folks? Back for our next installment in the watch-along of Cosmos: A Personal Voyage with Carl Sagan. We're up to episode 9. I did want to once again remind that this is a watch-along, meaning it's not just the episode by itself, and there will be times where I pause to comment and either offer whatever insight I may have or personal anecdotes and so on. Of course, I will try to keep that to a relative minimum, but this is a watch along. You're watching it with me, and it's a show I've known for a long time now, and I have very strong feelings about. And as has been happening in previous episodes of this watch along, I will at various points mention if I have any mixes that sample particular monologues from Carl. So in any case, the next episode is called Lives of the Stars, and indeed he will be speaking about the life cycles of different types of stars and how that may relate to us and to the cosmos more generally. So let's get to it. This is episode 9 of Carl Sagan's Cosmos: A Personal Voyage. Yes, before you ask, that is an apple, probably a Granny Smith. But of course, it does remind me that this episode features one of the most famous quotes from Sagan that sort of entered the pop culture lexicon. So we'll get that in a little while.
If you wish to make an apple pie from scratch, you must first invent the universe.
There it is. There are T-shirts with that line. I remember when I was first, taking an interest in this show and reading more about Sagan's career and so on. I'd go poking around online to see if there were any like shirts or memorabilia from Cosmos that I could acquire to rep or rock, as the kids say, or at least used to say like 20, 30 years ago. But yes, ultimately I remember seeing a T-shirt with him in this, famous characteristic jacket, and it was, sort of like a cartoon version of him. And on the shirt it said, "If you wish to make an apple pie, or from scratch, you must first invent the universe." And his meaning behind that, I think, will become clear, but I won't spoil it in advance.
If you wish to make an apple pie from scratch, you must first invent the universe. Thank you very much. Suppose I cut a piece out of this apple pie. Crumbly, but good. And now suppose we cut this piece in half, or more or less. And then cut this piece in half. And keep going. How many cuts before we get down to an individual atom? The answer is about 90 successive cuts.
So I talk about this in some like TV shows, like comedies and detective shows and so on. I am very like sensitive to ADR. Like I can just hear in many cases when a line has been dubbed in, and I believe he may have said a different number, whether 90, 70, whatever it was, or 80. Because in fact I think his mouth sort of forms 80. So I think they like did some calculations after and realized that it might be a slightly different number of cuts. And of course, that kind of measurement's going to be a bit imprecise. But yeah, the moment he says 90, you can like it. The audio quality of the word changes relative to everything else he says. So I remember when I first watched this, that stuck out to me. It's like, oh wait, I think that was ADR, which presumably means they must have, redone the calculations and realized it was slightly off when they first recorded it.
How many cuts before we get down to an individual atom? The answer is about 90 successive cuts. Of course, this knife isn't sharp enough, the pie is too crumbly, and an atom is too small to see in any case. But there is a way to do it. It was here at Cambridge University in England that the nature of the atom was first understood, in part by shooting pieces of atoms at atoms and seeing how they bounce off. A typical atom is surrounded by a kind of cloud of electrons. The electrons are electrically charged, as the name suggests, and they determine the chemical properties of the atom. For example, the glitter of gold, or the transparency of the solid that's made from the atoms silicon and oxygen. But deep inside the atom, hidden far beneath the outer electron cloud, is the nucleus, composed chiefly of protons and neutrons. Atoms are very small. 100 million of them, end to end, would be about so big. And the nucleus is 100,000 times smaller still. Nevertheless, most of the mass in an atom is in the nucleus. The electrons are, by comparison, just bits of moving fluff. Atoms are mainly empty space. Matter is composed chiefly of nothing. When we consider...
That's another one to wrap your head around. And obviously, our studies of quantum particles and quantum dynamics has enhanced and clarified some of our understanding about the microscopic world. But yes, the idea that atoms are, in terms of space, almost entirely nothing, just these very tiny, if admittedly featuring most of the mass nucleus or nuclei, surrounded by these, clouds of potential places where electrons can be. It's just crazy to think that, as he says, matter in terms of space and volume is composed almost entirely of nothing.
Are mainly empty space. Matter is composed chiefly of nothing. When we consider cutting this apple pie, but down beyond a single atom, we confront an infinity of the very small. And when we look up at the night sky, we confront an infinity of the very large. These infinities are among the most awesome of human ideas. They represent an unending regress, which goes on not just very far, but forever. Have you ever stood between two parallel mirrors in a barbershop, say, and seen a very large number of you?
To answer that question for myself, and long before I ever saw this series, I remember in one of the bathrooms in my home, the home that I grew up in had one of those, mirrored medicine cabinets, and then a big mirror in front of it. And I remember being fascinated as a kid, if I would like turn it at a certain angle, the successive number of me and, like a little bit of the medicine cabinet mirror, it would just like proliferate and sort of, it was almost like a fractal, if you will. And I remember thinking, like, that's crazy. Like, I didn't get how light worked. I had no sense of the propagation of photons and, physics and chemistry that are discussed and explained in this series. But I do remember being fascinated that I could bend the mirror or like, turn the medicine cabinet mirror at a certain angle where I would see literally scores, if not hundreds, of increasingly smaller me's in the image on the actual like full mirror.
Or between two parallel mirrors in a barbershop, say, and seen a very large number of you. Or you could use two flat mirrors and candle flame. You would see a large number of images, each the reflection of another image. You can't really see an infinity of images because the mirrors are not perfectly flat and aligned, and there's a candle or candle flame at least in the way, and light doesn't travel infinitely fast. When we talk of real infinities, we're talking about a quantity larger than any number. No matter what number you have in mind, infinity is larger. There's a nice way to write large numbers. You can write the number 1,000 as 10 to the power 3, meaning a 1 followed by 3 zeros. Or a million is written as 10 to the power 6, meaning a 1 followed by 6 zeros. There's no largest number. If anybody gives you a candidate largest number, you can always add the number 1 to it. But there certainly are very big numbers. The American mathematician Edward Kasner once asked his young nephew to invent a name for an extremely large number, 10 to the power 100, which I can't write out all the zeros in this page for because there isn't room on the page. The boy called it a Google.
And somewhere the founders of Google were like, oh, wait, let's copyright that. But yes, that is in fact where that company name comes from.
If you think a Google is large, consider a Googleplex. It's 10 to the power of a Google. That is a 1 followed not by 100 zeros, but by a Google zeros.
Which, like, it's a level that, again, defies simple human contemplation when talking about the universe of the very, very small or the very, very large. Our human brains that are comfortable with, macroscopic reality here on Earth and the sort of familiar scales of human existence, it is quite a challenge to wrap your brain around some of these quantities and volumes of, again, the very small and the very large. And yes, I know that Google is spelled differently from the company name, but as I said, I think that is the source of where they came up with the name.
10 to the power of a Google. That is a 1 followed not by 100 zeros, but by a Google zeros. Now, by comparison with these enormous numbers, the total number of atoms in that apple pie is only about 10 to the 26th, tiny compared to a Google, and of course much, much less than a Googleplex. The total number of elementary particles, protons, neutrons, and electrons, in the accessible universe is of the order of 10 to the 80th, so 1 followed by 80 zeros.
Think of that. Like, just, making up Carl Sagan or making up all the objects in a particular room. Think about how many protons and neutrons and electrons that entails. And then he's saying that all the elementary particles in the entire known universe is maybe 10 to the 80th. And you get a sense for just how big numbers like a Google or a Googleplex must be.
Still much, much less than a Google, and vastly less than a Googleplex. And yet, these numbers, the Google and the Googleplex, do not approach, they come nowhere near infinity. In fact, a Googleplex is precisely as far from infinity as is the number 1. We started to write out a Googleplex, but it wasn't easy.
That's number 1. I think this is a horn concerto by Mozart, if I'm not mistaken. But yeah, that's like maybe counterintuitive, but because of the nature of infinity, where there is no quantity or volume that can ever reach it, it is a truism that, again, the number 1 is just as far away from the quantity or volume of infinity as is a Googleplex.
Far from infinity as is the number 1. We started to write out a Googleplex, but it wasn't easy.
It's a very big number. Writing out a Googleplex is a spectacularly futile exercise. A piece of paper large enough to contain all the zeros in a Googleplex couldn't be stuffed into the known universe.
Again, it's like my first impression when I heard that is like, wait, like I get it's, astronomically, unfathomably large, but really, like, the universe, just the galaxy, just our solar system is a very, very big place. And yet we're saying that paper with writing at that scale that would actually include all the zeros in a Googleplex couldn't fit into the known universe. Like, my God.
Fortunately, there's a much simpler and more concise way to write a Googleplex. Like this. And infinity can be represented like this. This is the Cavendish Laboratory at Cambridge University, where the constituents of the atom were first discovered. The realm of the very small.
From the time of Democritus in the 5th century BC, people have speculated about the existence of atoms. For the last few hundred years, there have been persuasive but indirect arguments that all matter is made of atoms. But only in our time have we actually been able to see them. Here, the red blobs are the random throbbing motions of uranium atoms, magnified 100 million times. How Democritus of Abdera would have enjoyed this movie.
We pretty much take atoms for granted. And yet, there are so many different kinds, lovely and useful at the same time. Look.
I'm second guessing myself earlier if that was a Mozart horn concerto. I do think it was a horn concerto, but yes, I'm second guessing my placement of that composition.
There are some 92 chemically distinct kinds of atoms naturally found on Earth. They're called the chemical elements. Virtually everything we see and know, all the beauty of the natural world, is made of these few kinds of atoms arranged in harmonious chemical patterns.
Here we've represented all 92 of them. At room temperature, many of them are solids, a few are gases, and 2 of them, bromine and mercury, are liquids. They're arranged in order of complexity. Hydrogen, the simplest element, is element number 1, and uranium, the most complex, is element 92. Some elements are very familiar. For example, silicon, oxygen, magnesium, aluminum, iron, the elements that make up the Earth. Or hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur, the elements that are essential for life. Other elements are spectacularly unfamiliar. For example, hafnium, erbium, diprosium, praseodymium, elements we're not in the habit of bumping into in everyday life. By and large, the more familiar an element is, the more abundant it is. There's a great deal of iron on the Earth, not all that much yttrium. The fact that atoms are composed of only 3 kinds of elementary particles, protons, neutrons, and electrons, is a comparatively recent finding. The neutron was not discovered until 1932, and it, like the electron and the proton, were discovered here at Cambridge University. Modern physics and chemistry have reduced the complexity of the sensible world to an astonishing simplicity. 3 units put together in different patterns make essentially everything. A neutron is electrically neutral, as its name suggests. A proton has a positive electrical charge, and an electron an equal negative electrical charge. Since every atom is electrically neutral, the number of protons in the nucleus must equal the number of electrons far away in the electron cloud. The protons and neutrons together make up the nucleus of the atom. Now, the chemistry of an atom, the nature of a chemical element, depends only on the number of electrons, which equals the number of protons, which is called the atomic number. Chemistry is just numbers, an idea which would have appealed to Pythagoras. If you're an atom and you have just 1 proton, you're hydrogen. 2 protons, helium, 3 lithium, 4 beryllium, 5 protons, boron, 6 carbon, 7 nitrogen, 8 oxygen, and so on, all the way to 92 protons, in which case your name is uranium. Protons have
Myranium? I thought we agreed it was our ranium. Sorry, I just always have to make that joke with uranium.
8 oxygen, and so on, all the way to 92 protons, in which case your name is uranium. Protons have positive electrical charges. but like charges repel each other. So why does the nucleus hold together? Why don't the electrical repulsion of the protons make the nucleus fly to pieces? Because there's another force in nature, not electricity, not gravity, the nuclear force. We can think of it as short-range hooks which start working when protons or neutrons are brought very close together. The nuclear force can overcome the electrical repulsion of the protons. Since the neutrons exert nuclear forces, but not electrical forces, they are a kind of glue which holds the atomic nucleus together. A lump of 2 protons and 2 neutrons is the nucleus of a helium atom and is very stable. 3 helium nuclei stuck together by nuclear forces makes carbon. 4 helium nuclei makes oxygen. There's no difference between 4 helium nuclei stuck together by nuclear forces and the oxygen nucleus. They're the same thing. 5 helium nuclei makes neon, 6 makes magnesium, 7 makes silicon, 8 makes sulfur, and so on, increasing the atomic numbers by 2 and always making some familiar element. Every time we add or subtract 1 proton and enough neutrons to keep the nucleus together, we make a new chemical element. Consider mercury. If we subtract 1 proton from mercury and 3 neutrons, we convert it into gold, the dream of the ancient alchemists. Beyond element 92, beyond uranium, there are other elements. They don't occur naturally on the Earth. They're synthesized by human beings and fall to pieces pretty rapidly. One of them, element 94, is called plutonium and is one of the most toxic substances known. Where do the naturally occurring chemical elements come from? Perhaps a separate creation for each element? But all the elements are made of the same elementary particles. The universe, all of it, everywhere, is 99.9% hydrogen and helium, the 2 simplest elements. In fact, helium was detected on the sun before it was ever found on the Earth. Might the other chemical elements have somehow evolved from hydrogen and helium? To avoid the electrical repulsion, protons and neutrons must be brought very close together so the hooks, which represent nuclear forces, are engaged. This can happen only at very high temperatures, where particles are moving so fast that there isn't time for electrical repulsion to act. Temperatures of tens of millions of degrees. Such high temperatures are common in nature. Where? In the insides of the stars.
Atoms are made in the insides of stars. In most of the stars we see, hydrogen nuclei are being jammed together to form helium nuclei. Every time a nucleus of helium is made, a photon of light is generated. This is why the stars shine. Stars are born in great clouds of gas and dust, like the Orion Nebula, 1,500 light years away, parts of which are collapsing under gravity. Collisions among the atoms heat the cloud until, in its interior, hydrogen begins to fuse into helium, and the stars turn on. Stars are born in batches. Later, they wander out of the nursery to pursue their destiny in the Milky Way. Adolescent stars, like the Pleiades, are still surrounded by gas and dust. Eventually, they journey far from home. Somewhere, there are stars formed from the same cloud complex as the Sun 5 billion years ago, but we do not know which stars they are. The siblings of the Sun may, for all we know, be on the other side of the galaxy. Perhaps they also warm nearby planets, as the Sun does. Perhaps they too have presided over the evolution of life and intelligence. The Sun is the nearest star, a glowing sphere of gas, shining because of its heat, like a red-hot poker. The surface we see in ordinary visible light is at 6,000 degrees centigrade. But in its hidden interior, in the nuclear furnace where sunlight is ultimately generated, its temperature is 20 million degrees. In X-rays, we see a part of the Sun that is ordinarily invisible, its million-degree halo of gas, the solar corona. In ordinary visible light, these cooler, darker regions are the sunspots. They are associated with great surges of flaming gas, tongues of fire, which would engulf the Earth if it were this close. These prominences are guided into paths determined by the Sun's magnetic field. The dark regions of the X-ray Sun are holes in the solar corona, through which stream the protons and electrons of the solar wind on their way past the planets to interstellar space. All this churning power.
I do love this track. It's used in a number of different contexts over the course of the series, but especially when we're, learning some profound truths about the nature of, be it life, the galaxies, or in this case, stars and their fusion, their stellar wind, which again, I feel like this episode definitely takes some of the scientific concepts at play to a higher level, so it's a testament to Sagan's ability to convey these ideas and scientific truths, which again are difficult for our everyday human brains to contemplate, much less to understand quantitatively, empirically, but it's a testament to his ability to explain and provide insight in a way that even lay people can understand. So
the dark regions of the X-ray Sun are holes in the solar corona, through which stream the protons and electrons of the solar wind on their way past the planets to interstellar space. All this churning power is driven by the Sun's interior, which is converting 400 million tons of hydrogen into helium every second. The Sun is a great fusion reactor into which 1 million Earths would fit. Luckily for us, it's safely placed 150 million kilometers away.
It is the destiny of stars to collapse. Of the thousands of stars you see when you look up at the night sky, every one of them is living in an interval between two collapses. An initial collapse of a dark interstellar gas cloud to form the star, and a final collapse of the luminous star on the way to its ultimate fate. Gravity makes stars contract unless some other force intervenes. The sun is an immense ball of radiating hydrogen. The hot gas in its interior tries to make the sun expand. The gravity tries to make the sun contract. And the present state of the sun is the balance of these two forces, an equilibrium between gravity and nuclear fire. In this long middle age between collapses, the stars steadily shine. But when the nuclear fuel is exhausted, the interior cools, the pressure is no longer enough to support its outer layers, and the initial collapse resumes. There are three ways that stars die. Their fates are predestined. Everything depends on their initial mass. A typical star with a mass like the sun will one day continue its collapse until its density becomes very high. And then the contraction is stopped by the mutual repulsion of the overcrowded electrons in its interior. A collapsing star twice as massive as the sun isn't stopped by the electron pressure, and it goes on falling in on itself until nuclear forces come into play, and they hold up the weight of the star. But a collapsing star 3 times as massive as the sun isn't stopped even by nuclear forces. There's no force known that can withstand this enormous compression. And such a star has an astonishing destiny. It continues to collapse until it vanishes utterly. So every star is characterized by the force that holds it up against gravity. A star that's supported by the gas pressure is a normal run-of-the-mill star like the sun. A collapsed star that's held up by electron forces is called a white dwarf. It's a sun shrunk to the size of the Earth. A collapsed star supported by nuclear forces is called a neutron star. It's a sun shrunk to the size of a city. And a star so massive that in its final collapse it disappears altogether is called a black hole. It's a sun with no size at all. But on their ways to their separate fates, all stars experience a premonition of death. Before the final gravitational collapse, the star shudders, briefly swells into some grotesque parody of itself. With its last gasp, it becomes a red giant.
Some 5 billion years from now, there will be a last perfect day on Earth. Then the sun will slowly change, and the Earth will die. There is only so much hydrogen fuel in the sun. When it's almost all converted to helium, the solar interior will continue its original collapse. The higher temperatures in its core will make the outside of the sun expand, and the Earth will become slowly warmer. Eventually, life will be extinguished, the oceans will evaporate and boil, and our atmosphere will gush away to space. The sun will become a bloated red giant star, filling the sky, enveloping and devouring the planets Mercury and Venus, and probably the Earth as well. The inner solar system will reside inside the sun. But perhaps by then, our descendants will have ventured somewhere else. In its final agonies, the sun will slowly pulsate. By then, its core will have become so hot that it temporarily converts helium into carbon. The ash from today's nuclear fusion will become the fuel to power the sun near the end of its life in its red giant stage. Then the sun will lose great shells of its outer atmosphere to space, filling the solar system with eerily glowing gas, the ghost of a star outward bound. Perhaps half the mass of the sun will be lost in this way. Viewed from elsewhere, our system will then resemble the Ring Nebula in Lyra, the atmosphere of the sun expanding outward like a soap bubble. And at the very center will be a white dwarf, the hot, exposed core of the sun, its nuclear fuel now exhausted, slowly cooling to become a cold, dead star. Such is the life of an ordinary star, born in a gas cloud, maturing as a yellow sun, decaying as a red giant, and dying as a white dwarf enveloped in its shroud of gas.
And you heard what he said there about how in its later stages the fusion processes will change such that it's not just hydrogen, fusing into helium. So more on that coming, but yeah, I remember being very interested in the life cycles of stars, and at the time I was watching this, I ended up getting a book by, a completely unrelated book called Cosmos. Indeed, there is a book form of this series, and I think it was written maybe in conjunction with Andrian, but the book Cosmos I got was from many years later, and it was one of those oversized books where it's very big with large pages, and it talked in more detail, and admittedly it was from multiple decades after this, so I think some of the information was still yet refined, and I was fascinated by the physics and chemistry of the life cycles of stars. And ultimately, again, we're going to get more not only on that in this episode, but Sagan, of course, takes that to a human level and explains it in a way that is not just about the empirical data, but with philosophical meaning.
Suppose, as we traveled through interstellar space in our ship of the imagination, we could sample the cold, thin gas between the stars. We would find a great preponderance of hydrogen, an element as old as the universe. We would find carbon, oxygen, silicon. The most abundant atoms in the cosmos, apart from hydrogen, are those most easily made in the stars. But we would also find a small proportion of rare elements, praseodymium, say, or gold. They're not made in red giants. Such elements are manufactured in one of the most dramatic gestures of which a star is capable. A star more than about 1.5 times the mass of the sun cannot be a white dwarf. It may end its life by blowing itself up in a titanic stellar explosion called a supernova. There has been no supernova explosion in our province of the galaxy since the invention of the telescope, and our sun will not become a supernova. But in our imagination, we can fulfill the dream of many earthbound astronomers and safely witness, close up, a supernova explosion. Most of stellar evolution takes millions or billions of years, but the interior collapse that triggers a supernova explosion takes only seconds. Suddenly, the star becomes brighter than all the other stars in the galaxy put together.
I think that was the Rite of Spring, Stravinsky.
If a nearby star became a supernova, it would be calamity enough for the inhabitants of this alien system. But if their own sun went supernova, it would be an unprecedented catastrophe. Worlds would be charred and vaporized. Life, even on the outer planets, would be extinguished. In our ship of the imagination, we are now backing away from the star, but the explosion fragments, traveling almost at the speed of light, are overtaking us. Individual atomic nuclei, accelerated to high speeds in the explosion, become cosmic rays. This is another way that stars return the atoms they've synthesized back into space. The shockwave of expanding gases heats and compresses the interstellar gas, triggering a later generation of stars to form. In this sense also, stars are phoenixes, rising from their own ashes.
Yeah, that's crazy. So it's like the heat and the dispersed particles end up like supercharging other clouds of gas and dust, which can, again, like activate fusion processes and lead to a new generation of stars.
Another way that stars return the atoms they've synthesized back into space. The shockwave of expanding gases heats and compresses the interstellar gas, triggering a later generation of stars to form. In this sense also, stars are phoenixes, rising from their own ashes. The cosmos was originally all hydrogen and helium. Heavier elements were made in red giants and in supernovas, and then blown off to space, where they were available for subsequent generations of stars and planets. Our sun is probably a third-generation star. Except for hydrogen and helium, every atom in the sun and the earth was synthesized in other stars. The silicon in the rocks, the oxygen in the air, the carbon in our DNA, the gold in our banks, the uranium in our arsenals were all made thousands of light years away and billions of years ago. Our planet, our society, and we ourselves are built of star stuff.
Another one of those like spine-tingling moments where the connected nature of the cosmos is, I think, very profoundly explained by Carl. The idea that every element, heavier than helium, is made either in red giants or in the colossal and catastrophic supernova explosions of even larger stars. So that, as you said, like, the carbon in our DNA, the silicon, the gold in our banks, and the, uranium in our arsenals were all made in stars, millions of years ago, billions of years ago, and thousands of light years away. It's crazy.
Except for hydrogen and helium, every atom in the sun and the earth was synthesized in other stars. The silicon in the rocks, the oxygen in the air, the carbon in our DNA, the gold in our banks, the uranium in our arsenals were all made thousands of light years away and billions of years ago. Our planet, our society, and we ourselves are built of star stuff.
We're in a lava tube, a cave carved through the earth
by a river of molten rock.
To do a little experiment, we've brought a Geiger counter and a piece of uranium ore. Now, the Geiger counter is sensitive to high-energy charged particles, protons, helium nuclei, gamma rays. If we bring it close to the uranium ore, the count rate, the number of clicks, increases dramatically. We also have a lead canister here, and if I drop the uranium ore into the canister, which absorbs the radiation, and cover it up, I then find the count rate goes down substantially, but it doesn't go down to zero. What's the source of the remaining counts? Well, some of them come from radioactivity in the walls of the cave. But there's more to it than that. Some of the counts we're hearing right now are due to high-energy charged particles which are penetrating the roof of the cave. We are listening to cosmic rays. Every second they are penetrating my body and yours. They don't do much damage. Cosmic rays have bombarded the Earth for the entire history of life on our planet. but they do cause some mutations, and they do affect life on the Earth. The cosmic rays, mainly protons, are penetrating through the meters of rock in the cave above me. To do this, they have to be very energetic, and in fact, they are traveling almost at the speed of light. Think of it. A star blows up thousands of light years away in space and produces cosmic rays, which spiral through the Milky Way galaxy for millions of years until, quite by accident, some of them strike the Earth, penetrate this cave, reach this Geiger counter, and us. The evolution of life on Earth is driven in part through mutations by the deaths of distant stars. We are, in a very deep sense, tied to the cosmos.
Our ancestors knew this well. The movements of the sun, the moon, and the stars could be used by those skilled in such arts to foretell the seasons. So the ancient astronomers all over the world studied the night sky with care, memorizing and recording the position of every visible star. To them, the appearance of any new star would have been significant. What would they have made of the apparition of a supernova, brighter than every other star in the sky?
On July 4th, in the year 1054, Chinese astronomers recorded what they called a guest star in the constellation of Taurus, the bull. A star never before seen burst into radiance, became almost as bright as the full moon. Halfway around the world, here in the American Southwest, there was then a high culture rich in astronomical tradition. They too must have seen this brilliant new star. From carbon-14 dating of the remains of a charcoal fire, we know that in this very spot, there were people living in the 11th century. The people were the Anasazi, the antecedents of the Hopi of today. And one of them seems to have drawn on this overhang protected from the weather a picture of the new star. Its position near the crescent moon would have been just what we see here. And the handprint is perhaps the artist's signature. This remarkable star is now called the Crab supernova. Nova from the Latin word for new, and crab because that's what an astronomer centuries later was reminded of when looking at this explosion or remnant through the telescope. The crab is a star that blew itself up. The explosion was seen for 3 months. It was easily visible in broad daylight, and you could read by it at night. Imagine the night when that colossal stellar explosion first burst forth.
That's pretty impressive day for night photography there. Like normally, and you see in older movies, it's like it's clear that it's daytime, even though they're shooting it like as if it's night. And, it often doesn't really look like night. But that transition right there looked legit, as if everything just got dark.
Imagine the night when that colossal stellar explosion first burst forth.
A 1,000 years ago, people gazed up in amazement at the brilliant new star and wondered what it was. We are the first generation privileged to know the answer. Through the telescope, we have seen what lies today at the spot in the sky noted by the ancient astronomers, a great luminous cloud, the remains of a star violently unraveling itself back into interstellar space. Only the massive red giants become supernovas, but every supernova was once a red giant. In the history of the galaxy, hundreds of millions of red giants have become supernovas. The bit of the star that isn't blown away collapses under gravity, spinning ever faster like a pirouetting ice skater, bringing in her arms. The star becomes a single massive atomic nucleus, a neutron star. The one in the Crab Nebula is spinning 30 times a second. It emits a beamed pattern of light and seems to us to be blinking on and off with astonishing regularity. Such neutron stars are called pulsars.
Neutron star matter weighs about a mountain per teaspoonful. So much that if I had a piece of it here and let it go, and I could hardly prevent it from falling, it would effortlessly pass through the Earth like a knife through warm butter. It would carve a hole for itself completely through the Earth, emerging out the other side, perhaps in China. The people there might be walking along, minding their own business, when a tiny lump of neutron star matter comes booming out of the ground and then falls back again. The incident might make an agreeable break in the routine of the day. The neutron star matter, pulled back by the Earth's gravity, would plunge again through the rotating Earth, eventually punching hundreds of thousands of holes before friction with the interior of our planet stopped the motion. By the time it's at rest at the center of the Earth, the inside of our world would look a little bit like a Swiss cheese.
There are places in the galaxy where a neutron star and a red giant are locked in a mutual gravitational embrace. Tendrils of red giant star stuff spiral into a disk of accreting matter centered on the hot neutron star. Every star exists in a state of tension between the force that holds it up and gravity, the force that would pull it down.
And I think he talks about this, but yes, the situation you just talked about where a neutron star, the remnant of a supernova, now compressed essentially to the size of a city and, being one big atomic nucleus, when it accretes matter, pulled off of another star, eventually it gets to the point where it itself is, sort of caused to have a supernova, but it's like a different type of supernova than when a red giant star is so big that when it collapses, it explodes. And that's the difference between a type 1 and a type 2 supernova. Again, I think he talks about this, but...
Every star exists in a state of tension between the force that holds it up and gravity, the force that would pull it down. If gravity were to prevail, a stellar madness would ensue, more bizarre than anything in Wonderland. Alice and her colleagues feel, more or less, at home in the gravitational pull of the Earth, called 1G, G for Earth gravity. What would happen if we made the gravity less or more? At lower gravity, things get lighter. Near 0G, the slightest motion sends our friends floating and tumbling in the air. Little blobs of liquid tea are everywhere. Curious. If we now return the gravity to 1G, it's raining tea, and our friends fall back to Earth. I've been to a couple of parties like that myself. At higher gravities, 2 or 3 Gs, say, things get really laid back. Everyone feels heavy and leaden. Except by special dispensation, the Cheshire Cat. As a kindness, we remove them. At thousands of Gs, trees become squashed. At 100,000 Gs, rocks become crushed by their own weight. At all these gravities, a beam of light remains unaffected, continuing up in a straight line. But at billions of Gs, Even a beam of light feels the gravity and begins to bend back on itself. Curiouser and curiouser. Such a place, where the gravity is so large that even light can't get out, is called a black hole. It's a star in which light itself is imprisoned. Black holes were theoretical constructs speculated about since 1783. But in our time, we've verified the invisible. This bright star has a massive unseen companion. Satellite observatories find the companion to be an intense X-ray source called Cygnus X1. These X-rays are like the footprints of an invisible man walking in the snow. The X-rays are thought to be generated by friction in the accretion disk surrounding the black hole. The matter in the disk slowly disappears down the black hole. Massive black holes produced by the collapse of 1 billion suns may be sitting at the centers of other galaxies, curiously producing great jets of radiation pouring out into space. At high enough density, the star...
And at the center of our own galaxy, in a location that is, I think, dubbed Sagittarius A, there is a supermassive black hole, which again, like in terms of the actual, what we would call physical space, is, you know, nearly imperceptible. It's like a point of volume, but its mass is, you know, far beyond, again, like normal human contemplation. But yes, even in our own galaxy, there is a supermassive black hole at the center.
Winks out and vanishes, radiation pouring out into space. At high enough density, the star winks out and vanishes from our universe, leaving only its gravity behind. It slips through a self-generated crack in the space-time continuum. A black hole is a place where a star once was.
Here we have a flat two-dimensional surface with grid lines on it, something like a piece of graph paper. Suppose we take a small mass, drop it on this surface, and watch how the surface distorts or puckers into the third physical dimension.
Gravity can be understood as a curvature of space. If our moving ball approaches a stationary distortion, it rolls around it like a planet orbiting the sun. In this interpretation, due to Einstein, gravity is only a pucker in the fabric of space, which moving objects encounter. Space is warped by mass into an additional physical dimension.
The larger the local mass, the greater is the local gravity, and the more intense is the distortion or pucker or warp of space. So, by this analogy, a black hole is a kind of bottomless pit. What would happen if you fell in? Well, assuming you could survive the gravitational tides and the intense radiation flux, it is just barely possible that by plunging into a black hole, you might emerge in another part of space-time, somewhere else in space, somewhen else in time. In this view, space is filled with a network of wormholes, something like the wormholes in an apple, although by no means is this point demonstrated. It is merely an exciting suggestion. If it is true, then perhaps there exist gravity tunnels, a kind of interstellar or intergalactic subway, which would permit you to get from here to there in much less than the usual time, a kind of cosmic rapid transit system.
We cannot generate black holes. Our technology is far too feeble to move such massive amounts of matter around. But perhaps someday it will be possible to voyage hundreds or thousands of light years to a black hole like Cygnus X1. We would plunge down to emerge in some unimaginably exotic time and place, our common sense notions of reality severely challenged. Perhaps the cosmos is infested with wormholes, every one of them a tunnel to somewhere. Perhaps other civilizations with vastly more advanced technologies are today riding the Gravity Express. It's even possible that a black hole is a gate to another and quite different universe.
The lives and deaths of the stars seem impossibly remote from human experience, and yet we're related in the most intimate way to their life cycles. The very matter that makes us up was generated long ago and far away in red giant stars. A blade of grass, as Walt Whitman said, is the journey work of the stars.
That's such an awesome line. Like, I remember when I first heard that, I was like, oh man, I've heard of his writing, but I did not know he was astronomically conversant and was, expressing such profound ideas in poetic language. But yeah, I do at this point have to note that earlier Sagan, when he was talking about, black holes being the product of extremely large stars as they compress to the point where they disappear entirely. I know I use that in a mix. I want to say astonishing. And there's been a couple other Lives of the Stars. I think I did a mix by that name. So yes, I've been trying to keep that to a minimum in this particular episode. But yes, there's been a few monologues, and I think there's another bit coming up here. But I love that a blade of grass is the journey work of the stars.
Possibly remote from human experience, and yet we're related in the most intimate way to their life cycles. The very matter that makes us up was generated long ago and far away in red giant stars. A blade of grass, as Walt Whitman said, is the journey work of the stars. The formation of the solar system may have been triggered by a nearby supernova explosion. After the sun turned on, its ultraviolet light poured into our atmosphere, its warmth generated lightning, and these energy sources sparked the origin of life. Plants harvest sunlight, converting solar into chemical energy. We and the other animals are parasites on the plants, so we are, all of us, solar powered. The evolution of life is driven by mutations. They're caused.
I apologize. I think solar powered is the name of the mix that I use this particular monologue in.
Animals are parasites on the plants, so we are, all of us, solar powered. The evolution of life is driven by mutations. They're caused partly by natural radioactivity and cosmic rays, but they are both generated in the spectacular deaths of massive stars thousands of light years distant. Think of the sun's heat on your upturned face on a cloudless summer's day. From 150 million kilometers away, we recognize its power. What would we feel on its seething, self-luminous surface or immersed in its heart of nuclear fire? And yet, the sun is an ordinary, even a mediocre star. Our ancestors worshiped the sun, and they were far from foolish. It makes good sense to revere the sun and the stars.
Because we are their children. We have witnessed the life cycles of the stars. They are born, they mature, and then they die. As time goes on, there are more white dwarfs, more neutron stars, more black holes. The remains of the stars accumulate as the eons pass. But interstellar space also becomes progressively enriched in heavy elements, out of which form new generations of stars and planets, life and intelligence. The events in one star can influence a world halfway across the galaxy and 1 billion years in the future. The vast interstellar clouds of gas and dust are stellar nurseries. Here first begins the inexorable gravitational collapse, which dominates the lives of the stars. Massive suns may evolve through the red giant stage in only millions of years, dying young, never leaving the cloud in which they were born. Other suns, longer-lived, wander out of the nursery. Our sun is such a star, as are most of the stars in the sky. Most stars are members of double or multiple star systems and live to process their nuclear fuel over billions of years. The galaxy is 10 billion years old enough to have spawned only a few generations of ordinary stars. The objects we encounter in a voyage through the Milky Way are stages in the life cycle of the stars. Some are bright and new, and others are as ancient as the galaxy itself. Surrounding the Milky Way is a halo of matter, which includes the globular clusters, each containing up to 1 million elderly stars. At the centers of globular clusters and at the core of the galaxy, there may be massive black holes ticking and purring, the subject of future exploration. We on Earth marvel, and rightly so, at the daily return of our single sun. But from a planet orbiting a star in a distant globular cluster, a still more glorious dawn awaits. Not a sunrise, but a galaxy rise.
I apologize to briefly interrupt this, but people may know, anyone who's familiar with Carl and so the legacy of this series, eventually, and I'm forgetting the name of the people who did it, but a music track was made using this monologue, and I think it's called a more glorious dawn or something to that effect. I have it on vinyl, so at some point I'll do a reaction to it, and it features also like a voice that I think is done in like the Stephen Hawking, it's sort of like a robotic voice, but yes, it samples this section of monologue. Still more glorious dawn, sorry.
We on Earth marvel, and rightly so, at the daily return of our single sun. But from a planet orbiting a star in a distant globular cluster, a still more glorious dawn awaits. Not a sunrise, but a galaxy rise, a morning filled with 400 billion suns, the rising of the Milky Way. An enormous spiral form with collapsing gas clouds, condensing planetary systems, luminous supergiants, stable middle-aged stars, red giants, white dwarfs, planetary nebulas, supernovas, neutron stars, pulsars, black holes, and there is every reason to think, other exotic objects that we have not yet discovered. From such a world, high above the disk of the Milky Way, it would be clear, as it is beginning to be clear on our world, that we are made by the atoms and the stars, that our matter and our form are determined by the cosmos of which we are a part. I only have a moment, but I wanted you to see a picture of Betelgeuse, that's what it's called, in the constellation Orion, the first image of the surface of another star. But the most exciting recent stellar discovery has been of a nearby supernova in a companion galaxy to the Milky Way. We are here witnessing chemical elements in the process of synthesis and have had our first glimpse of the supernova through a brand new field, neutrino astronomy. And we're now seeing, around neighboring stars, disks of gas and dust just like those needed to explain the origin of the planets in our solar system. Worlds may be forming here. It's like a snapshot of our solar system's past. And there are so many such disks being found these days that planets may be very common among the stars of the Milky Way.
What a sunrise, or indeed, what a galaxy rise that would be, right? And indeed, I believe I did a mix called Galaxy Rise, though I don't know if it's on my YouTube. But yes, so again, I think this episode, takes some of the required thinking and technical detail of the scientific information to a higher level. I think, again, Sagan does a great job of making it understandable, such as these crazy and large-scale concepts can be to the layperson. But I think it's moved to another level relative to the first couple episodes. Masco's Bakery, clearly where we saw that opening sequence with the apple pies. It didn't even have that final part with the filmed at Sagan Studios. But yes, ultimately, as I said, the physics and chemistry of this episode reveal just in one way how far human science and endeavor to understand the universe in which we live had advanced, even 40, 50 years ago. But also the staggering simplicity, which, again, the idea of quantum physics and the way we understand it now making it a bit more complicated, notwithstanding the elemental simplicity in terms of the composition of nearly all matter in the universe is one of those not only astonishing truths, but the profound nature that we are made of star stuff, or as Neil deGrasse Tyson would rephrase the sentiment in his version of Cosmos, stardust, I think is, not only scientifically valid, but philosophically inspiring and profound. So again, I love the way that this show is very technical, and yet the humanistic nature of it comes through very deeply and consistently. So again, shout out to Carl and to all the other people involved, especially Stephen Soder and Andrew Yan, as well as Adrienne Malone and so on. But yes, ultimately 3 more episodes, right? 10, 11, 12, no, 13. That's right. So we have 4 more episodes to go, and then we'll be on to the first of the Neil deGrasse Tyson series. So let me know what you think of this episode, and I will see you next time. Peace.